Hello. Today we're going to study inductive reasoning and pattern recognition. This is something you're probably going to be good at because it's something people do naturally. If you don't believe it, take a look at an astronomy book sometime. Look at all those constellations. The Greeks connected dots. They saw the stars as dots, they connected them, and they saw a bear or a guy with a sword and hundreds of other things which most of us would say aren't there. For instance, Ursa Major doesn't look like a big bear to me. Neither does Ursa Minor. Ursa Minor doesn't look like a small bear to me. It just looks like a group of stars. The only constellation I've seen that actually looks like anything to me is the Big Dipper. It actually does look like the silhouette of a ladle. Other than that, people spot patterns whether they are there or not. If that weren't true, ink blot tests would be of no use. That's what an ink blot test is based on. What pattern do you see in this completely random shape, I guess you could say. In the old days, TV sets had interference patterns. There was just a whole bunch of dots floating around on the screen, and people saw all kinds of things inside those random movements of dots. Hasn't happened recently, but every decade or two, somebody sees the face of the Madonna in a tortilla. They kick a tortilla, they see a bunch of dots, and go, oh my, the Persian Mary, right there, her face in the tortilla. That's how bad we are at pattern recognition. We see them when they aren't even there. Well, not bad, good, I guess you could say, depending on how you look at it. So spotting patterns isn't going to be a really tough thing for you to do most of the time. Unless, of course, you're a squirrel and you just snuck into the classroom. If you're a squirrel, get out. You're not going to understand this. Only people are into inductive reasoning. And what does that mean? Well, it means that we go from the particular to the general. That's the usual definition of inductive reasoning. In other words, you've got some simple examples, and you jump to a conclusion, more or less. It's not always good to jump to a conclusion, but that's what inductive reasoning and spotting patterns tends to lead to. And a lot of times it's very good. Most of technology and modern advancement has been a result of some form of inductive reasoning, spotting a pattern in something. Hunters a long time ago spotted migration patterns. That's how they knew where to hunt. They knew when the animals were coming by. They spotted the pattern. They knew where the water was going to be and when, because they spotted the pattern. They knew that at times of the year certain water holes would be dry. And it was that way every year. That was the pattern, and they spotted it quickly and easily. That's what people do. So this section is going to be really easy for you. In fact, as a child, inductive reasoning probably has a lot to do with how you learned about your world. You see a dog. It barks. You see another dog. It barks. You don't have to see very many dogs before you come to the conclusion, dogs bark. You're using inductive reasoning when you do that. See? It's easy. And the statement, dogs bark, well, that's called a conjecture. You have the reasoning, which leads to a conjecture. Sometimes you're jumping to an erroneous conclusion. Then it's called a jumping to a conclusion, not a conjecture. Otherwise, if it makes sense and it's good, you call it a conjecture. One more thing you need to understand about inductive reasoning, conjectures, and spotting patterns, and that is counterexample. And that's also something that I'm sure you're already very familiar with. I bet every time your parents tell you to do something you don't want to do, you come up with a counterexample for their reasoning. Counterexamples are simple. For instance, if I say, all dogs bark, all I have to do is go find one quiet dog, and that disproves the conjecture. The existence of only one is enough to disprove it. Counterexamples are very simple, a very quick, easy way to prove the inaccuracy or error of a conjecture. And we're going to do some in the problems we work out. But counterexamples are extremely simple to come up with usually. All people are over 6 feet tall. Well, all you have to do is go find somebody who's less than 6 feet, and you've disproved that conjecture. All people are good at math. Well, I'd like to believe that. But if you could find one person who wasn't good at it, that would disprove the conjecture. Well, this is all really pretty simple. We'll just go through some of these problems here and see how they work out. You get an idea of what I'm talking about. Okay, here are 3 conjectures. And what we're going to do is quickly and easily prove that they are wrong. How? Simplest way in the world. This is about the easiest proof you're ever going to see. It's proof by counterexample. If the product of 2 numbers is positive, then the 2 numbers must both be positive. Well, let's see here. We could try 1 times minus 2. Ooh, that's less than 0, so that's negative. How do we get a positive number? Well, what about 1 times 2? Well, that's greater than 0. But these both numbers are both positive. Well, so far the conjecture is true. Well, let's try minus 1 times minus 1. And what do we get? 1. Whoa, wait a minute. That's greater than 0. That's positive. I think we just found a counterexample. We've got 2 numbers, which are not positive, but their product is positive. So, there's our counterexample. Oops. There's our counterexample. And we're all done. We just proved that this is wrong. All prime numbers are odd. Well, remember, a prime number is one that's not divisible by anything except 1 in itself. So what are the prime numbers? Well, 1, 3, 5, 7, 11. Ooh, wait a minute. I left 1 out there. 2. 2 is a prime number, but it's also even. In this case, most prime numbers are odd. If you remove 2 from the set, they would all be odd. But 2, well, there's our counterexample. 2 is a prime number. It's even, so this is false. If the product of 2 numbers is even, then the 2 numbers must both be even. Well, 2 times 2 is 4. Oh gee, they're both even. What about 2 times 3? Well, 1's even and 1 isn't. That's 6, but 6 is even. So, oops, there's one counterexample. This one here, to tell you the truth, I can only come up with one counterexample, and that was the number 2. Here and here, there are an infinite number of counterexamples. All you have to do is pick one. Just pick one, and you're all done. See? Real easy. Real simple. Now here's another one of those find the error problems. I don't know why it has to be a student all the time. Let's say a lawyer came up with this, okay? How about a city councilor? Geez, they get things wrong all the time. No matter what city you're in, that's a safe bet. So here we go. All angles are acute. Well, boy, oh boy. There's all kinds of things wrong with that reasoning. One of the problems, I would say, is if all angles were acute, why would there even be a word for it? Why not just call it an angle? There'd be no point in having a second way of describing angles if they all were that. But they aren't. Now, you want a counterexample? Okay, there's a couple of easy ones. Remember, we've defined all kinds of angles. Acute, obtuse, right, and straight. Draw any one of them you want, and that's a counterexample, for instance. Whoa, yeah, okay. It's not horizontal, but it's straight. And then we take off like that. Now that big angle there, that's not acute. So, boom, we're done. We just proved that this is wrong. And this lawyer here, he doesn't know what he's talking about. This spotting patterns. Although by virtue of being human, you are naturally good at it, it's still not an easy thing to do. For instance, in numbers, boy, I mean, it might take you a while to spot the fact that this is 3 times this, and this is 3 times this. So this number is probably something we multiply by 3 to get 81. Well, 81 divided by 3 is 17. Oops, I hope not. And of course it's 27, not 17. Pardon me. If it turned out to be 17, I would be in big trouble. What's 1/3 of 27? Well, that would be a 9, wouldn't it? And 1/3 of 9 is 3. See, 3 times 3, that's 9. 3 times 9, 27. 3 times 27, 81. 3 times 81. So that's the pattern. Just start with this and multiply each number you get by 3. And it turns out that the first number in the pattern would actually be 3. The only problem with this business of spotting patterns, I can't give you a formula for it, a way to spot a pattern. There's no simple way I can tell you, this is how you always spot a pattern. It could be geometric, it could be numeric. There isn't one actual formula or theorem that will tell you how to always spot a pattern. It's something you just have to do. But remember, the more you do things, the better you get. So if you want to get good at spotting patterns, all I can say is practice. Okay, now what we have here is every batter's dream. A pitcher who is totally predictable. Why is he predictable? Well, I'm not sure what these little paths of the balls have to do with anything. They really don't. We're looking for a pattern here. So it's a fastball and then a curve, and then 2 fastballs and 2 curves, and then 3 fastballs. I would guess 3 curves. So the next 5 pitches would be curve, curve, curve. That's 3 curves. And then fastball, fastball. And in this case, he's going to throw 4 fastballs, followed by 4 curveballs. They only asked for the next 5, so that would be these here. And if you play baseball, you probably spend a lot of time watching the pitcher and trying to figure out what his next pitch would be. And if you found one like this, you'd be in heaven. Now here's one that's interesting. It's the sort of thing that's done all the time. Sometimes accurately, sometimes not so much. Make a conjecture that could be true. Did I mention before, these guys are really smart. You don't have to say it's true, it just could be true. After all, something could have happened between 03 and 04, which either increased the rate at which email increased, you get what I mean, or it decreased the rate at which email increased, or it may have even stopped increasing, just level off right here. But guessing from this more recent data, the next year, our best prediction would probably be up in here. However, as you keep going farther and farther away from your data, your predictions become less and less reliable. For instance, you follow this straight line and you're up here around, see, I don't know, 23 trillion if I got this scale right, and I'm pretty sure I didn't. But it's this accurate number up here when you get out to, say, 2020. Following the straight line, this number is probably, say, 25 trillion, give or take a couple. It's hard to say. And that's probably not accurate. Why not? Well, the simple answer is nobody knows the future. Down in here, I don't know how much texting was going on right in here. I'd say not much. But as time went on, texting became more and more popular and became much easier because of the invention of telephones, which were much easier. They're practically just computer tablets now. Well, in here, it got easier for texting, and then of course there was Twitter, Facebook, and lots of other inventions which would have obviated email in many circumstances. So chances are that this straight line is completely wrong. It's probably, had sort of a curve to it around somewhere in here. Who knows where the curve started? And then leveled off, and heck, it may have even started to reduce, just leveled off at some number way below what you would get up here. Then again, maybe not. It could have kept going. Heck, it could have followed some, it could have just taken off and followed some really steep curve like that. We don't know. It would depend on what happened in here. Normally, when you're making predictions with time as a variable, you count the most recent data points the most. In other words, give the most weight to this. Here we got a straight line. Here it's more of a curve. If we follow this, we'd go boom, way up there. The more recent data points form a straight line, so we just extrapolate that line, but not for more than a year or so. After that, chances are these predictions would be grossly inaccurate, and that's for you to find out. Go ahead, go online, check it out, see what the use of person-to-person email was by year up to 2019, 2020, whatever year you're doing this in, 2030, whenever, and see what actually happened. It's a good thing to do because you're going to hear things like this. Radio, television, tons of people make predictions about the future. Now, as a math guy, I'm pretty good at spotting numbers that don't sound right, and I'm pretty sure that they didn't do a very good job of prediction. But if you don't want to go get a degree in math, you could look at it this way. If somebody somewhere says he can predict the future, some aspect of the future, not necessarily everything, but some aspect of it, if he can pick some quantity and predict what it's going to be in 20 years, my question to him is, why worry about 20 years? Why don't you just pick football, predict who's going to win the Super Bowl next year, and make yourself a fortune? In other words, if you had any ability to predict the future accurately and truly, you would already be rich. And you talk to people who became rich who started without much, and most of them did it because they saw what was coming, and they did, in a sense, predict the future, at least in their industry. They knew what was going to happen, or at least had a better guess than everybody else. So when people try to tell you that they know what's going to happen in 20 years, ask them why they aren't millionaires. On the other hand, if it's a millionaire and he tells you what's going to happen, he might be right. And I think it would be a really good idea to go online and see how this really worked out. Did it really continue on with a straight line? Did it take off at a much steeper curve, or did it level out? You find out. Okay, here's one that you shouldn't have any trouble with. Let's take a look at what we're doing here. These squares are 1 by 1. That makes it pretty easy. Find the distance around each figure. That would be like that. And putting them in a table is a good idea. It makes it real easy to spot the patterns, if there is one. So let's start with number 1. And since these are, I'm not sure what you actually call the numbers, I'll just call it I. For I equal to 1, I equal to 2, etc. And distance around, well, if you didn't have all this stuff on the inside, technically, this would actually be a polygon. It certainly wouldn't be a regular polygon, but it would be a polygon. So we'll just call this P for perimeter. So when I is 1, what do we have? Well, all the way around is, of course, 1, so we just got 4. What about this one? Well, let's see here. We get 2 here and 2 here, that's 4. And then each one of these little corners accounts for 2, and there are 2 of them. So we've got 2, 4, 6, 8. And how do we get that? Got 2 here, and then there's, well, let's go to this one. The pattern will be more obvious. Put the 2 over here and the 8 here. You're probably starting to spot something already. Now we've got 3 units along the side here, 3 units along here. That's 6, and then 2 for each of the corners, and there are 3 corners. So we got 3, 6, 8, 10, 12. There are 12 up there. And now with this one, so we got 4 here and 4 here, and then 1, 2, 3, 4 of these corners, which each account for 2. So you noticed each time we do this, we have 2 sides that are actually equal to I. So that's 2I. And then we have I corners, which each account for 2 sides. And for instance, this one, we get 4 and 4 is 8, 10, 12, 14, 16. And that coincides with this here. 2 times 4 is 8, and 4 times 2 is 8. That adds up to 16. And we could obviously rewrite this as 4I. As you look at the table here, you might spot real quick that P is just 4 times this number here, the I. On the other hand, you could look at it this way and say that it's going to be 2 times whatever I happens to be, plus there will be I corners, and each one accounts for 2. So it's 2 times I plus I, 2, which does add up to 4I, but doesn't exactly tell you what's going on. This is another example of the fact that it's easy to find patterns, because here's one pattern, which would just be, this one leads you to say just 4I, without any particular reason for it. This one gives you 2I plus I2. In a sense, that's another pattern. These patterns, of course, result in the same answer. They'd have to, or they would just be an incorrect pattern. But this is an example of how easy it is to spot patterns, and how often people see patterns. You can have more than one pattern, or you can spot more than one pattern in a sequence. And the distance around the 20th figure in the pattern, well, I think we got that pretty well figured out, don't we? We just multiply that by 4 and we get 80. So, real simple. I just made a rough graph here. That's a lot easier because, anyway. And this appears to be a straight line to me. We've only got a few complete points. We got -3, -5 down here. We've got 5, 11, and we've got 15, 31 up here. And we're looking for a pattern, which in this case will be an equation of a line. We've got a straight line here. So we've got, how do 5 and 11 compare to 15 and 31? Well, 2 times 5 is 10. If you add 1, you get 11. 2 times 15 is 30. And if you add 1, you get 31. What about down here? 2 times -3 is -6. If you add 1, you get -5. Well, I think we have the equation of our line. It is 2x plus 1. So if we were to fill this in, for instance this one here, 2x plus 1, well, I think x would have to be 0, wouldn't it? 2 times 0 plus 1, that's 1. Plus 1. Well, 2 times 7 is 14, plus 1 is 15. 2 times 12 is 24, plus 1 is 25. Describe the pattern in words. Well, I guess I just did. It's a straight line, and the equation is 2x plus 1. Again, I can't give you a formula for spotting patterns. You just have to try things out and hope really hard that they didn't try to kill you. I mean, you could have ordered pairs here that make perfect sense. There is a pattern, and you could spend 10 years trying to find the pattern. You might never do it. Well, you probably wouldn't take it that long. There are tricks for finding patterns that are numerical, and they actually involve doing graphs and taking logarithms, see if you can straighten out the graph. For instance, if the graph were to look like that, and then you squared it, you might get something. Well, that's not right. You can find a way to, say, take the log or the square root or something else when you've got a curve, and instead modify it and turn it into a straight line. And that sounds really weird, but in much more advanced mathematics, you'll be able to do that, and it's not that big a deal. So there are ways to find patterns, but with the tools you have at the moment, you pretty much just have to spot it and try to guess. So they better give you kind of reasonable problems. I mean, if they give you something where it turned out the pattern was y equals cosine of x plus y squared, you got a real mess there, and you're just the table of values isn't going to tell you much. You'd have to be really, really sharp to spot that once you drew your x's and your y's in a table, and you'd be looking at it and saying, geez, I don't know what the heck that is. Hardly anybody would. So hope for simple straight lines or extremely simple curves. Most of the times, I think you're going to end up with something like this is going to hopefully turn out to be a straight line. It's really, really hard to find the functional representation if it turns out to be something really messy like this, or there are an infinite number of things it could be. Okay, here's one that seems, I think you would say this was fairly easy. Can you spot the pattern? If you sell no tickets, what's your income? Nothing. One ticket, 25 cents. Because they're 25 cents per ticket, right? And you go right down the line here. 5. Do you spot the pattern? Well, I think it would be hard not to spot the pattern. I mean, gee whiz. 4 tickets, you get $1. 3 tickets, you get 75 cents. 1 ticket, 25 cents. Well, I think it's pretty obvious that 25 cents times the number of tickets sold is going to be how much money you took in. I don't know what class is doing this. 25 cents a piece for raffle tickets would just about pay for a field trip to the soda machine, wouldn't it? Oh well, I guess that's their problem. So write an equation for your income Y if you sold X tickets. Well, that's like dirt simple. Come on, it's like 0.25 times the number of tickets sold. That equals Y. As far as graphing it goes, well, as you already know, this is not only a straight line, this is a straight line that goes through the origin. Notice there's no plus or minus in here. It's just a direct relationship. When X is 0, Y is 0. And that makes sense because it says so right here. So you're, if you were to graph it, it's not going to have a very steep slope at all. It has a slope of 1/4, which that might even be too big, but that's about as well as I can draw. And this is roughly x over 4, right? 1/4 x, 0.25x, same thing. If your class paid $14 for the raffle prize, your class is extremely cheap. How many tickets does your class need to sell to make a profit? Well, let's figure out the break-even point. Not just because it's easy for this problem, but in all financial mathematics. When you want to know where the profit starts, you always find the break-even point, and everything to the right of that goes in your pocket. So what's 14 divided by 0.25? Well, that's the same as 14 over 1/4, which equals 4 times 14. That's 40 plus 16 is 56. That's what I get. Yeah, 56. So if they sell 56 tickets, they break even. If they want to make money, they have to sell more than 56 tickets. How many tickets do you need to sell to make a profit of $50? Well, remember, we're not going to just take in $50. The profit has to be $50. And I'm going to go with this number up here since they didn't give us any other price. So let's make some room here for some more calculations. So to make a profit of $50, first we have to break even. So we've got to pick up $14. And then, after we've broke even, we pick up an extra $50, so that would be $64 altogether we would have to take in. We've already figured out up here that dividing by 0.25 is the same as multiplying by 4. So, in order to figure out the actual profit, number of tickets we have to sell. We already know the profit is $50. But we have to sell $64 worth of tickets. So we have to multiply 4 by 64. To 56. We sell 256 tickets. We will take in $64, and that will be $50 of profit. It's a very practical problem because these types of computations get used all the time. And here is a very popular pattern. This pattern comes up all the time, called Fibonacci numbers. And if you study more biology, you'll probably run into them. You actually probably run into them in physics too, especially biology. For some reason, it's a very natural sequence. And what is it? Well, let's see here. We got 1, 1, and then 2. And then there's a 3 and a 5. Well, a 5 is 3 and 2. See, 8 is 5 and 3. 13 is 8. Oh, wait a minute. I think I see what's going on here. 1 and 1 is 2. 1 and 2 is 3. Aha. So, each number is the sum of the 2 previous numbers. The next 3 numbers in the pattern, well, that's pretty easy. 89 plus 55. Just get your calculator and write it in. So finding the next numbers is pretty easy. I didn't even use a calculator. We just wrote it out here so you can see what's going on. We take 89 and 55 and get 144. So we put it in here. Now we take 144 plus 89, and that's this one. That's our next number in the sequence. Now we take 233 plus 144, and that's 377, and it just goes on. There's no end to this. So we've got the next 3 numbers. Now, this pattern has been used to describe the Nautilus shell. Okay. Now, I'm going to let you guys do it yourself. Go ahead and find various examples of Fibonacci numbers. I will tell you one thing. Leaf clusters tend to come in Fibonacci numbers, usually in 3 and 5. For instance, clovers. Clover is a tiny little plant with leaves you see down there in the lawn. It's about what, half an inch high, if that. And you may have heard the expression that a four-leaf clover is lucky. Well, I don't know how lucky they are, but they are rare. They're not that easy to find. Why? Because they normally come in groups of 3 or 5. The four-leaf clover would be a mutant, so to speak. It happens. They do exist. But there are very few of them, and that's why they call them lucky. They're rare. Most of the time it's 3 or 5. And that's the reason four-leaf clovers are called lucky, because they're rare. And they're rare because of this Fibonacci sequence here. Well, that's the end of this one. I think you understood this pretty easy. Even I didn't get very confused this time.